Hi and welcome back to a new episode. Today's episode is about multiple linear regression in R. We will focus in diagnostics. That means that we are going to fit a multiple linear regression model and we're going to test the assumptions once we have fit our model. Among other things, we will learn to load the data, split the data into training and testing sets, build the model, make prediction with a given model, measure the model performance, how to test linear model assumptions, and how to eliminate these problems. And finally, we will compare our first model and our second model. This and more we're going to talk next in R. Now, then we're going to talk about multiple regression and its diagnostics with R. Now, first of all, we have to prepare the data you're going to use, of course, and for that, I'm going to let you to use the package mass where we're going to find this very useful information about house pricing in Boston. So you can see, we will talk about different variables. Today's episode is not about exploratory data analysis. I'm going to talk about this one superficially. As you can see, we have different variables where our final variable to measure or to predict is med. That is the median value of a house given certain attributes or features, as we can see here, for example, age of the house, distance to different train stations, and so on. Then we can see the structure of data. As you can see, it's numeric, and certain variables are integers. Well, what we can do? What are the different machine learning steps in this case? Well, we're going to split our data into training, testing set, because we want to measure our model performance with unknown information. Let's set a seed we can replicate our results. For that, we're going to use, as you can see here, I'm going to show you, we need the library tidyverse. This library will allow us for data manipulation and Caret for different workflow that we need in machine learning. Given the library Caret, we can create data partition. And for tidyverse, we use the pipeline. As you can see, we're going to pass Boston Med, the different information in Boston Med, and we're going to create this partition where this p equals 0.8 means 80% of our data is going to be for training, and the rest, that 20%, is going to be for testing. Okay, and we run this, and we will see the training sample here to my right. Well, I didn't run tidyverse. Okay, now that is done, then we can create our data partition. And as you can see here, I'm going to run what is training samples. You can see it to my right, but I'm going to show you here training samples. Training samples are different indices. That means that in training samples, we're going to take the different indices for the data we're going to use for training, and the rest, the one who doesn't appear in training sample, is going to be the one for testing. And as you can see, because we have indices, we can take training samples to our training data from Boston, and we pass it to training data. And with a negative sign, we get rid of those indices, and we take those indices who doesn't appear in training sample. That means that those observations or rows in Boston who are not in training samples. Now we have our training and testing data that we can use for fitting our model and for predicting new values. Let's see. How do we fit a model? Well, in R we just call LM. The function LM will allow us to fit a linear model. In this case, multiple linear model. As you can see, med is our outcome, our response variable, then with the tilde, and then that dot, we're just saying use all the other variables in the data, in this case, train data. And as we can see, you just call summary to see the results. You see here, for example, we have an adjusted R squared of 0.72. Okay, and we can also check other values here. For example, if different variables are significant or not, given the column PR. That is for the p-value. If that variable, in this case PR, the column has a value less than 0.05, the variable is significant, or the feature, for example, chas into ZN crime, that means that it's significant, right? 0.05. What else we can see here? Okay, now we're going to make predictions to test more about our model performance. In this case, that 0.72 that I was talking before, in this case, R squared, the adjusted or the usual R squared is for the training data. Now for the testing data, we just call predict, and we pass that the object in this case is our model, model 1, and with a pipeline from dplyr, we use predict. And you can see predictions now. In predictions, we have the predicted values for new data. And we create data frame for just to see the performance, different metrics that we use in regression. In this case, the RMSE is the median square error, but the root, of course. You can use MSE if you want to, or you can use the root. The root, square root of means square error. And R squared is measured for, and R squared is used for measuring how well the model fits our data. In this case, we can see we are talking about predictions. Prediction in this case is new data. That means that predicted values, and test data method is the real values. That means the given observations we want to test with the predicted values. Okay, and then we can see the model performance. You can see here, oh, 72. Not so bad. Why I'm saying not so bad? Because for our model was 73. So that means that our model is not overfit or underfit. The R squared for training and for testing are similar. So that means that our model is just doing fine. Perfect, not necessary. There are better models, maybe, and that's what we're going to see. But okay, but because we're working with multiple linear regression, we need some linear model assumptions to test. Do you know which are those assumptions we're going to diagnose right now? Okay, we call them line, and they are the linearity of variables with outcomes. That means that the outcomes is linear dependent with different variables. The independence of residuals, normality of residuals, and equality of variance, what we call homoscedasticity. What does it mean? Okay, independence of residuals means that one given observation doesn't depend of other observation. For example, in time. Normality of residuals is that we're going to calculate if we have a, or the residuals have a normal distribution. Remember that curve or shape bell. And equality of variance means that in a scatter plot, the different residuals by the dependent variable is just scattered around. Okay, that there is no pattern. We don't see any pattern, for example, a curve just going up and then decreasing. No, we just want to see the dots around scattered. The different points are going to be scattered around. Let's see. How do we do this fastly in R? We just call the model with plot. Plot model 1, you will see to my right, and we will have here different plots. As you can see here, is residuals versus fit. This one will help us for the homoscedasticity. So you can see we have some problems here because we have this observation here and the other group of observation here, and we can see that they are not helping with that pattern in our data or not pattern. So I'm going to, as you can see here, I just can detect there are some observation there, and we call them 373, 381, and we will check other plots. Let's see. Here, for example, is the normality. What is the normality in this case? The normality should be all around this line here. So you can see there are some observations that are out. Why? Because maybe there are outliers to our data. Then, in this case, the residuals don't fit or don't follow a normal distribution. It's simple to see, right? Okay, what else? What else can we see with this plot? We can see scale location. In this case, as you can see here, it's talking about standard residuals. It's just to standardize the residuals that you previously saw. So you can see you still have these observations that are disturbing our scatter plot. Finally, we can see how different observations are. We can see here how different residuals are showing us how different observations are having greater influence than other ones in our calculation of our model. You can see here, for example, 381, the observation of 381, and these other observations. And if you can take, I was taking note, this one over here. So you can see cube distance is showing us the influence of these value observations in or how was our model fit. Then we have to get rid of these observations or to understand why they are appearing. In this case, you have to see that all of them are behind 0.2, and that observation is greater than 0.4. Its leverage is greater than 0.4. So we have to get rid of them. All of these observations, I saved them here in a vector called M, and this is super important. I noticed that these are row names. These are not the number of the observation, but the row names. Why? Because we divide our information in training data and test data. Then, now that observation 381 is not exactly the 381 in our original data in Boston data set. Then we have to be very careful with this, and then we're going to use the function row names. My row names are in, look, as you can see here, percentage in, that way, if the trained data, one of those row names are in this subset we call M, so we are not going to use it. Where I'm saying don't use it, they here, different than. That means that if you find something that is here, don't take that observation. We get rid of that. And I'm going to call that train data claim. Okay, perfect. Now, let's check now the residuals. We previously saw how our normal plot was telling us, okay, you are not working with residuals who are following a normal distribution. Let's check the box plot. You can see here, it's important to notice these observations. They are out of the maximum allowed value. Then we're calling them outliers. The box plot, as you can see, it looks like it's following a normal distribution, but those residuals that we call outliers are disturbing and having great influence in how the model was calculated. Then we can get rid of them. How? We just save the information in VP. I call it this object VP. And I'm saying, okay, if those residuals are out, as you can see, I'm going to call it VP out, and you will see what is coming. So you can see all those are the observations who are outliers for that in the box plot. We can get rid of them because that means that those residuals are too big compared with the other ones, right? And you say, okay, all those residuals, all the residuals in our model, as you can see, we have here 506. We are gonna compare with those residuals who are out in our box plot. We call them outliers. So if you find them in, as you can see, wish, what means wish? Wish means the number of the row, not the row name. Super, it's different. As you can see, there are two different ways to call this. Because I want to extract the number of the observation, different than the row names, different, right? And we save this in an object called n, it's a vector. We have 24 observations. We're going to eliminate n. You can see here, minus n. We're gonna eliminate those observations in that vector. Where? In the data clean, because that's then our new set, our new data frame. Perfect. So you can see here, we're passing from, I'm gonna show you, I'm gonna call dimension train.data. We originally had 407 observations, and now here we have 380. That means that we got rid of 27 observations that are gonna result in a new model. New residual plot. Once we eliminate that, how does it look like for the model one? For the model one, you can see here, it's look super different, right? They don't have too many outliers. Those are too close to be called outliers. And why this one appears as outliers? Because it's a new box plot, right? Super important. Now we are gonna build a new model with our transform or our change data set. As you can see here, I call data clean instead of train data. And we use all the variables that were that dot there, and our dependent variable or outcome is met, median value price of the house. And model 2, summary. Remember, do you remember how was our R square for training data? It was 0.73. So you can see our R square for our model 2 is better. We went from 0.73 to 0.82. The fit in our model has improved. Okay, super important. And plot 2. Now let's discover if we really change the assumptions or if the assumptions are met in our new model. Let's check that. Let's see. Okay, does our scatter plot looks better? Yeah, I think yes. Remember that there were some branches out here. There was a cloud of points around that were disturbing the pattern or not pattern in our plot. This looks way better. Let's see about the normality plot. This is still having problems, right? As you can see here. But remember, normality is the less of our problem. So we can just ignore it and continue checking if the homoscedasticity is met or not. Here, you can see the standardized residuals are showing us that our scatter plot is okay. It's just fine. You can see that our different points are scattered around. So that's great. I'm gonna make a zoom on this, where you're gonna see better. Here it is. So you can see our scatter plot looks way better now. And finally, we can see the influence points with that cook distance. As you can see, I don't see any observation. Maybe this one here, but it is not marked. I don't know why not. As you can see, we have a better looking plot now. It's look better, right? It's not marking any point actually. So it's look better. Can we conclude that our model is or our model met all the assumptions? Yes, our model meets all the assumptions because normality is the less of our problem. So it's not gonna be so perfect, but it's just great. And we can continue with our model performance. As you can see here, model 2, predict test data. That hasn't changed at all, right? It's new data, remember? So super important. Predictions. Let's see the first 5 predictions. So you can see the medium price value. And now we're gonna compare the R square. Remember 0.72. 0.72. And that it's even better than the model that was fit 7.2 is even better than the R square for the model 1 when it was fit. Okay, that means that with the training data it was 73 and this one is 77. That means that it's even better, right? Okay, as you can see, of course there is a difference between R square for training data and testing data in the model 2. In model 2, the R square for the training data was 0.72 and this one is 77. Of course, the data is looking better, the model fits better, but we can still see that there is no overfitting, right? The model is doing fine, the model meets all the assumptions and it's not overfit. So that is a great model, right? Not the best, not necessary, okay? And finally, let's compare these assumptions. And let's see here, we're going to compare model 1, model 2. We can see here the plot for measuring the homoscedasticity in our two models. Model 1 looks completely different than model 2. Here I can see that the data is more scattered around than here. And you can see that even in the axis. Here 20 and here, for example, 40. As you can see, is 15 to 40. That means that our model has improved not only by its performance, but how it's meeting the assumptions. What is coming next? Well, for next episode, we're going to talk about multicollinearity as well as standard coefficient, how to measure which variable has more impact in our linear model fit. That's what we're going to talk about more here with R and Mark. See you.